All right, thank you, Lisa. So as Lisa mentioned, my name is Jeremy Twitchell, and I work at the Pacific Northwest National Laboratory. My main responsibility at the lab is on the Office of Electricity's Energy Storage Program in the equitable regulatory environment space. So the work that we do is trying to understand the regulatory barriers to energy storage and emerging practices, best practices for reducing or eliminating those barriers. Next slide, please. So I'll be giving you an overview of energy storage technologies today. So a little bit about different technologies, some of their relevant strengths and then trade-offs. Then we'll talk a little bit about the services that energy storage can provide and some of the ways that we value those. Then we'll look at energy storage in regional markets, specifically in MISO in this case, and then a brief word about storage in microgrid applications. Next slide. And okay, one more, please. So the key takeaway here when we're talking about different types of energy storage is that energy storage comprises multiple technologies. And those technologies have different performance characteristics, different operational limitations. There are a lot of trade-offs. So there's three main types of energy storage. The first one here is mechanical. This is where we're taking electricity and we're storing it in the form of potential energy that we'll later use to generate more electricity. So in the case of pump storage hydro, we're using that electricity to pump water uphill, then later we release that water back through a generator to generate electricity. In compressed air energy storage, we're using electricity to compress air, and then later we're expanding and warming that air to power a generator. And in the case of flywheels, we're using electricity to wind them up one way and then releasing them to spin the other way and generate electricity. So the first two there, pump storage, hydro, compressed air energy storage, those are long duration technologies. These can be constructed to do 8 hours or more of discharge, especially in the case of pump storage hydro. Pump storage hydro has a better round trip efficiency. That's how much energy comes out relative to how much we put in. Very long cycle life. Both those technologies, though, not very flexible. They can't respond to those momentary changes from one moment to the next in the grid, things like frequency regulation. Flywheel is kind of the opposite of the other two. Very short duration, 15 minutes top, incredibly flexible, good round trip efficiency, but because of that short duration, they're basically limited to those moment-to-moment applications like frequency regulation. Next slide, please. So electrochemical storage, here we're storing electricity in the form of chemical bonds that we're later releasing to recapture that electricity. Lithium-ion batteries, flow batteries, sodium batteries. Different characteristics, different trade-offs here. Lithium-ion obviously has a distinct advantage right now in terms of its commercialization with vehicle demand, creating supply chains, creating competition, creating lower costs. Some limitations, however, safety concerns with fires, recycling challenges. Flow batteries, you lose some of that. You don't have the same fire risk. You do have high recyclability. One of the primary challenges we've seen with flow batteries, though, is that they are incredibly complex systems. There's pumps, there's machines, and engineering a device that can effectively and efficiently move these chemicals around for 15, 20 years is proven to be quite a challenge that we're still working our way through. Sodium batteries are kind of in between the other two. Moderate durations, 4 to 6 hours, moderate round trip efficiency, moderate cycle life. The challenge with sodium is that you have to operate it at a very high temperature because the sodium exists in a molten state, which creates operational challenges and some safety risk. Next slide, please. Then finally, we have thermal energy storage, and this is where we're using electricity to heat or cool, air or some other medium for energy management or electricity production. So in the case of ice thermal storage, this is a rapidly growing technology, little different from the others in that we're not putting electricity back on the grid. We're taking electricity and then we're using it to offset future needs, by pre-cooling, by preheating, shifting that HVAC demand. Concentrating solar, long duration applications, 6 to 12 hours, really good round trip efficiency, fairly good life, some flexibility, not as much as you'd get from a battery, for example, but because it is ultimately powered by a generator, it does have some ramping and some flexibility characteristics. So if we could put up the poll question, please. Thank you. So question here is, we all know that battery energy storage has grown rapidly over the last few years, but from a grid perspective, from the amount of energy storage we have on the grid, how much of that is currently provided by battery technologies? Oh, this audience knows their stuff. That is correct. It's only about 4%. Next slide, please. Yeah, so we've got a little over 24 gigawatts of installed energy storage on the US grid at the moment. The vast majority of that, about 93%, comes in the form of pumped hydro storage. Batteries come next at about 4%, followed by thermal and compressed air. This is changing rapidly. The first time I made this slide about a year ago, batteries weren't even 2%. And based on what's currently in the pipeline to be commissioned by the end of the year, I expect we'll probably be somewhere between 5 and 6% by the end of the year. So rapidly growing. Of that battery technology that we have on the grid to the right there, lithium ion, the vast majority of it, about 88%, followed by lead acid, nickel, sodium, and then finally flow. Next slide, please. This is just a slide I threw in to point you to the report that's hyperlinked at the bottom down there. This is one that some of my colleagues did to look at various energy storage technologies and really understand how they differ operationally and what would their costs be if you compare them all on an apples to apples basis. And I just wanted to call your attention to that first row under lithium ion, the capacity cost. That's just the battery itself, and you'll see in parentheses there that currently that's estimated to be about $189 per kilowatt hour. So you may have seen news articles, industry press lately talking about how lithium ion has broken that $200 per kilowatt hour barrier. Next slide, please. And there's 4 animations if you just want to go ahead and click through those and get those up there. Probably an easier way to do it. Thank you. To actually install a battery, to interconnect a battery to the grid, you have to have a lot more than just the battery itself. You need to have a power conversion system. Batteries operate on a direct current. So you need a power conversion system to move things from DC to AC and vice versa. You need balance of plant operations. You need all the controls, the switches. You need physical infrastructure. You need HVAC, especially if it's a lithium ion battery. You need those environmental controls. Construction and commissioning, you have to build that thing. And the point of all this, there's you see at the bottom of that all-in cost of the installed cost of a battery, best estimate right now is around $469 per kilowatt hour. So when you look at just those battery costs, which have been falling rapidly, it's important to remember that you're only talking about roughly 40% of the overall system costs are represented in that battery pack. Next slide. And next, one more. Thank you. So as everyone I'm sure is aware, energy storage can do a lot of things across the entire grid infrastructure. On the generation side, it can provide capacity for resource adequacy, it can provide energy, it can provide various ancillary services, regulation, frequency response, operational reserves, spinning, non-spinning reserves. As a transmission asset, it can provide thermal management, it can provide congestion relief, and it can also defer infrastructure in some instances. On the distribution system, voltage support, maintaining the voltage necessary for electricity to move through the system. Conservation voltage reduction, distributed generation integration, increasing hosting capacity, managing flows, and also infrastructure deferral again. And then finally, on the customer side, behind the meter, you've got rate management, demand charge reduction, power quality, and of course, resilience backup power. Next slide. Now, the values of all these services are highly locational. They depend on a lot of things. They depend on tariff structures. They depend on local grid characteristics. They depend on market rules, on utility needs. So This is from a report that some of my colleagues did a couple years ago where they just looked, it's basically a gigantic literature survey where they just looked at all the valuation of energy storage technologies that they could find at the time to understand what are the different values of these different services in different regions and different points of the grid. And so as you can see there is a lot of variation for these services. And so the key takeaway here is that when you're trying to really understand the value of an energy storage asset, you need modeling capabilities that can do two things. They need to be able to granularly understand those benefits that are available to the system. You know, what is the benefit? What is the value of frequency regulation? What is the value of deferring a transmission line? And again, those are going to be highly locational. But then you also need the modeling capability to understand what are the operational characteristics of this device. Lithium ion in particular is very sensitive to how you use it. If you push it hard, if you discharge it quickly, you get lower round trip efficiency, you put more wear and tear on the battery. And so having a device that can do both those things, understand the economic value, but also the technical limitations, and then optimize on those two fronts is key to be able to identify the value of energy storage. Next slide, please. We've also been doing some work lately with this different paradigm of embedded energy storage. And if you think about electricity, it's unique among all the commodities that we use in that its supply chain was developed without a storage component. So anything else you use, food, water, natural gas, you know, it has that storage capability built into the supply chain. Things like warehouses, granaries, reservoirs, whatever they may be, and that embedded storage creates significant value to the system and to customers. It basically acts as a buffer between mismatches in supply and demand. It stabilizes prices, it protects customers. So one of the questions that we're starting to wrestle with is, now that we do have the ability to ubiquitously store energy storage across the grid, should we retrofit the grid with that capability? So, you know, to date, we've been adding energy storage kind of, you know, on the margins to kind of retrofit the grid with some degree of resilience, some degree of flexibility. But the idea here is if we treated energy storage like just a grid asset, the same way we think about a transformer or a substation, then instead of trying to add on to make the grid flexible, we would just make the grid flexible. So there's a hyperlink there to the first report we did in this series. We're working on a couple others that you can see where to find them later on. Next slide, please. So conceptually, this is the type of value that embedded energy storage can provide to the grid. This is a very simple demonstration down to the clip art that I used to put it together. But let's assume that we have a city that has an average demand of 1 million cubic feet of natural gas, but then it peaks to 1.5 million cubic feet. Then we have electric demand that's on average 100 megawatts, but then peaks to 125 megawatts. Well, if we compare how we design those two systems on the natural gas side, we can put a storage facility somewhere in the system so that upstream, we only need to size the system based on that average demand, you know, just enough size to meet those average demands. Then that storage facility can store the excess so that when we are in that peak condition, we only need to have the downstream portion sized to that 1.5 million cubic foot need. But if you contrast that with the electric side, we don't have that flexibility. If our peak demand is 125 megawatts, we have to design the entire system, generation, transmission, distribution, to meet that 125 megawatt demand. Even if we're only in that peak condition for a few hours of a year, the entire system has to be demanded to meet it. So the value is that where we have embedded storage on the natural gas system, we can more optimally design it. We can reduce system costs and, you know, have some efficiencies that we don't have available to us on the electric side now. Next slide. So, you know, it's an interesting idea, but there's a lot of questions that we're trying to work through here. You know, on the regulatory side, you know, we don't have standards that would justify this type of investment. You know, there's nothing like this in our current reliability standards. There's no such thing as a resilience standard. So, you know, there's no clear entryway for this type of usage of energy storage. Planning processes, bulk power system planning process to regional transmission planning system or processes, they're not They've historically been very slow to include new technologies. There's not really any clear requirements or mechanisms for new technologies to work their way into those processes. There's ownership questions. If this is embedded infrastructure, then it does have significant cybersecurity concerns, operational control needs, and who would own it? Is there even a mechanism by which third parties could participate in embedded energy storage? Compensation, how would you pay for this? If it's not participating in markets, is it just a regulated asset? And how do you justify? We all know this regulatory world very well. If there's not a justified need, then you can't make a case for that. And again, where there's no underlying standard that requires this type of usage, there's really no way to make that case. And then finally, metrics. How do you even measure this? How do you measure how effective it is? How do you measure its effect on the system and whether it's actually reducing system costs and improving operations? And then, on the valuation side, another issue we're starting to think about is, how do you quantify those grids, or excuse me, those benefits, and then how do you compensate the device for paying for them, or for providing them? Next slide, please. So moving on to storage in regional markets. So the Federal Energy Regulatory Commission, FERC, has two primary areas of authority over the electric grid. First is on the market side, regulating the market design and operations within the deregulated markets, which you can see there on the left. And then on the other side, the transmission side, FERC has authority over transmission system planning, operations, and rate making in all regions with interstate transmission. So even if there's not a deregulated market, like all these vertically integrated utilities out west that do operate interstate transmission systems are subject to FERC regulation on the transmission side. Important to point out, I went to graduate school in Texas, and I have professors who will kill me if I don't point out that Texas, because it does not have, the ERCOT region, because it does not have interstate connections, is not subject to FERC authority in either way. But the important note here is that FERC has used both of these lines of authority, the market side and the transmission side, in recent years to improve access for energy storage. Next slide, please. So on the market side, FERC issued Order 841 a couple years ago, and the crux of this order was FERC telling these deregulated markets that they had to reduce the barriers to energy storage participation in their markets. So FERC identified 7 specific criteria that the ISOs and RTOs had to meet. They had to create participation models for energy storage, make storage available or eligible to participate in all applicable markets, allowing it to do things like frequency response and potentially resource adequacy. And as they're doing this, they have to account for the unique operational characteristics of energy storage. Make sure that they've accounted for that and how the markets are designed, how products are designed, allowing asset owners to maintain their own state of charge, manage how they bid into those markets. And then also set a minimum size that's no greater than 100 kilowatts. Next slide. So focusing on MISO's implementation of Order 841. So MISO created this new resource type, the electric storage resource. They complied with FERC by saying that it can self-schedule, determine how and when it bids into markets. It has to be able to respond to a 5-minute dispatch signal from the ISO. So these have to be fast responding devices. The bids that storage devices have to submit are fairly substantial. There's 35 different things that they have to submit in their bids. Things like how much they're willing to pay to charge, how much they need in order to discharge, their ancillary service bids, startup bids, and then things like operational characteristics like ramp rate for the battery, discharge rate, the operational stuff. And then if a storage device is not selected in the day-ahead market process, then it is eligible to participate in the reliability assessment commitments where applicable. Next slide, please. So FERC accepted MISO's initial filing, but did request an additional compliance filing to clarify a few things. The big one with MISO was, so FERC had said that any resource, there was a minimal size for resources that could not be greater than 100 or smaller than 100 kilowatts. Excuse me, greater than 100 kilowatts. And so MISO did that, but MISO also put a cap on the number of those smaller facilities that can participate in the market. And FERC denied that, told them to remove that cap. That was the main issue that came out of that first filing. A couple other details you can see there. The compliance filing was accepted, but FERC actually requested another compliance filing to add some additional clarity about how MISO would handle metering and compensation for distribution connected energy storage that's also providing retail services. And so that second compliance filing is pending. Next slide. So on the transmission side of the house, oh, sorry, there was a poll there. So the idea here is trying to understand, what do you see the primary value of energy storage being in your state? Are you looking at it for renewables integration, for providing ancillary services on the grid, peak shaving, resilience? So if you could please let us know. Wow, interesting. Lots of interest in renewables integration. Okay. Great, thank you. So the transmission side of the house, FERC, well, this was prompted by a couple cases that FERC did back in 2008 and 2010. In both these cases, there was a pump storage hydro developer that came to FERC and said, hey, we think that we should be a transmission asset, and we would like a declaratory order to that effect. FERC said yes to one and no to the other. And if you dive into those proceedings, there's a whole lot of nuance as to why FERC came to those differing conclusions. But over the years, as these cases were cited in other proceedings, it became clear to FERC that a lot of that nuance had not been perceived. So they put out this policy statement in 2017 to clarify their view on this. And they said energy storage can be a dual use asset. And that's where it's a regulated transmission asset that also provides competitive market services, and that it can earn revenue from both operations, subject to these principles. It can't double recover its costs. It can't have unfair access to markets. There can't be any adverse impacts on the bidding process. And the ISO's independence must not be compromised. So basically, FERC said when the asset is operating in transmission mode, the ISO controls it. When it's operating in competitive mode, when it's operating in generation mode, operations revert to the owner, and the owner is responsible for putting in those bids and meeting its obligations. Policy statement is not binding, doesn't require anyone to do anything. CAISO, the California ISO, and MISO were actually the only two regional markets that initiated proceedings in response to this policy statement. Next slide, please. And it's really interesting. So MISO's proceeding was initiated about a little over a couple of years ago, and it identified the policy statement as one of its driving factors. Interesting to note that CAISO and MISO took completely divergent approaches to this. CAISO focused on enabling dual-use energy storage, and they set aside that question of how do we identify storage in the transmission planning process. CAISO said that's not what we're doing here. We're interested in this dual-use question. MISO went the opposite route. They ultimately decided, okay, we're going to set aside the dual-use question. We're going to focus on storage as a transmission asset. So MISO's storage is a transmission asset only. I put that in wrong. I just realized that transmission only asset, SATOA, clarified that where storage is selected through a transmission planning process, it's only a transmission asset. It's not eligible for market participation. If it wants to provide market services, it should come in as a generation asset. But what SATOA did, what this filing did that has not been done in most regions though, is clarify the process by which energy storage will be considered in regional transmission plans, and adding some additional clarity and transparency for how those analyses will be performed and how those decisions will be made. Next slide, please. So quick example of how storage can be provided, how storage can serve as a transmission asset from MISO. So the 2019 transmission expansion plan was actually the first MISO plan to identify energy storage as a transmission asset. This is actually only the second time it had happened anywhere. CAISO did it the year before in 2018. So near Waupaca, I'm probably saying that wrong, sorry, Wisconsin, they identified a contingency scenario, an N-1 scenario, where if a transmission line near Waupaca went out of service, the entire region would be cut off. And so they looked at their options, and they could install an additional circuit, add some redundancy in the area for $13.1 million, or they could add an energy storage system coupled with some line segmentation, some capacitors on the line. That would achieve the same outcome, that would maintain the Waupaca region in the event of that line outage at $12.2 million. So as the least cost option, it was selected. The expected in-service date is in December 2021. So important to remember that this is a transmission asset only. It will be recovered through MISO's FERC-approved transmission system rates, and it will not participate in energy markets. Next slide. So moving quickly to storage and microgrids. Thank you. So the paradigm that we've been operating under for resilience, for backup power, is generator based. You know, if I'm a facility, or if I'm a homeowner that wants to have backup power, I go out and I buy a generator. That generator provides me energy and capacity, but I don't have very many options. I probably don't have any options to participate in the grid, to provide cell services back to the grid. You know, my energy and capacity from my generator isn't particularly cost effective. It's not particularly easy to put back on the grid. So I absorb all those costs as the homeowner, as the facility owner. I have to buy the device, I have to buy and store the fuel, I have to do the maintenance. And so that adds up, that's expensive. And so traditionally, resilience has largely been limited to facilities where it's mission critical, hospitals, military bases, sensitive manufacturing facilities, places like that. But now with energy storage, we have this new paradigm where we can take that storage device, and then we can take that generator, we can take our distributed generation, you know, distributed solar, distributed wind, and we can use the storage device to shape all that generation. So now we're not just providing capacity and energy, we can also provide regulation, arbitrage, operating reserves, and you know, now we can provide valuable grid services. So we have increased opportunities to participate in the grid. And by doing so, by providing those services, we can earn offsetting revenue that reduces the cost of the system, thereby making, you know, these resilience projects, these resilience investments cost effective to larger groups. So now you're starting to see resilience take off at places like schools, community centers, dispatch centers, police departments, much bigger group investing in that now. Next slide. So don't need to speak to these, just wanted to leave a few questions, a few examples of the type of questions that states that policymakers and regulators can be asking in these processes as they're participating in them, as you're reviewing utility filings, participating in regional proceedings, things like that. Next slide. And then, you know, just wanted to leave you with a few resources for additional information about energy storage. That first group up there, you can see a few reports talking about energy storage, particularly in microgrid applications. That fourth one down, the planning considerations for energy storage and resilience applications. That's that graphic a couple slides ago about increased opportunities for resilience because of energy storage comes from that report. And then we walked through some of the planning considerations, you know, what it would look like from a planning perspective to consider some of these applications for energy storage and resilience. And then at the bottom there, you can see links to a few laboratory websites and other resources. And you know, I know we don't have a lot of time today, but I'm happy to take any questions anyone might have. My contact information's there, and appreciate the opportunity.
Thanks, Jeremy. You actually did really well for time. So Andrew, you can take more time as you need it. We actually have, I think I misspoke earlier, we actually have a total of 75 minutes for the session. And so, you know, feel free to take more time. We're looking for questions in the chat box. If you have any questions for Jeremy or Andrew, we'll take them following Andrew's presentation. Thanks, Andrew.
Okay, great, thanks. So good afternoon. I am Andrew Mills, a research scientist in the Electricity Markets and Policy Department at the Lawrence Berkeley National Laboratory. I'm going to talk about potential roles for storage in integrating variable renewable resources and also the emerging commercial interest in hybrid renewable plants. The goal of this is to share some of the insights from our research that can inform discussions about use cases for storage and important factors to consider. So I'll first talk about integration, and this section will primarily focus on the challenges of integrating variable renewable resources into the grid. Integration challenges include the variability of resources and also their contribution to resource adequacy. Variability is associated with the changes in supply within the operating hour or over multi-hour events. Uncertainty, on the other hand, is due to forecast errors, maybe in the day ahead or also closer into real time. A consequence of the variability and uncertainty is that the actual supply of generation will deviate from what was originally scheduled. And covering these deviations can require flexible resources to quickly respond, or it might require system operators to hold resources in reserve to cover those deviations. Actually, can you go back a couple slides? There you go. Yeah, go ahead and keep it on this one. Thanks. The fact that generation from variable resources is not aligned with times of greatest system needs leads to a lower contribution towards meeting resource adequacy requirements. So in many regions, the contribution of wind to resource adequacy might be only something like 25% or less of its nameplate capacity. The contribution of solar is higher often, but still it might be somewhere in the range of about 50% of its nameplate capacity. And then we see experience with high penetrations of solar in California that shows how the timing of greatest risk of outages can actually start to shift from the hot sort of summer afternoons into the early evening after the sun sets. So I'll talk about both of these two issues here and then describe some of the research that we're doing on how storage might be used to address these challenges. Next slide. One thing to keep in mind is that variability and uncertainty are inherently part of power systems due to the varying load. And so variable renewables increase this variability and uncertainty, and managing that can impose additional costs. Go ahead and go to the next slide. Over the past 2 decades, numerous studies have been conducted across the US and internationally to understand these integration costs of wind and solar. The resulting integration costs that you see from these studies differ across the studies for many different reasons, including differences in the mix of resources in the region. So that might include things like how flexible is the generation that's in that region. It also can differ because of whether these costs arise for a utility that's its own balancing authority, or if that utility is part of a larger coordinated regional system. And then we just see differences in how the studies themselves define and calculate these integration costs. And one of the places that we see these costs often discussed is in the context of integrated resource planning. And the reason is that standard grid planning models may not capture the full extent of this variability and uncertainty of renewables. And so to address this gap, detailed studies are often used to estimate the costs of these particular aspects that are not directly captured in the planning models. And I'll show some of those results from studies on the next slide here. Go ahead and flip to the next slide, please. Yeah, there you go, thanks. So most wind integration studies find that the costs associated with managing this additional variability and uncertainty of wind are below about $5 per megawatt hour of wind energy. There's a few exceptions to this, and that tends to happen when you have smaller utilities that are their own balancing authority, and that's more common in the Western US. The other thing that's interesting to note about this is that you don't see that these costs necessarily dramatically increase with penetration levels, that a number of studies that have done multiple penetration levels don't necessarily see a real steep rise, although you've seen that in some particular earlier studies. Next slide, please. There's a smaller number of studies that have estimated these integration costs for solar. And one thing that we see is that they tend to show a general range of costs that are somewhat in the same ballpark of what we've seen for wind. The particular study here in dark blue that's marked APS Argonne 2013, that was based off of a study that involved researchers from the Argonne National Lab, Berkeley Lab, and then the National Renewable Energy Lab. So I'll talk just a little bit more about the results of that particular study in the next slide. And again, one of the things that sort of is raised by this is why are those costs not considerably higher than you might expect, given that variability and uncertainty. Next slide, thanks. And one of the things that's clear is that if you look at individual power plants, you can see dramatic variability due to passing clouds, and that this cloud cover can oftentimes be hard to predict. So the red lines in these charts here show the solar output from 32 different simulated PV plants on a relatively clear day with the parts that are on the left, and then a relatively, like a partly cloudy day on the right. And if you look at some of these individual sites, you can see that production from these plants can just drop off in minutes at that individual site. So what we did was the study itself focused instead on strategies and costs for managing the solar at the aggregated level of the balancing authority. So we took the output from all of those same plants and saw that when we aggregated it, that it could become much more smooth across all of those 32 plants in the entire utility footprint. And in particular, that rapid drop-off in production that we could see at a single plant didn't really appear in the aggregate profile, and that's what's shown in the black lines, even on that partly cloudy day. So as a result of this, when we went and ran the study at what sort of additional incremental reserves might be required to manage this variability and uncertainty, we saw that those costs, again, would come in from somewhere below that $5 a megawatt hour range that we've seen from a number of studies. Next slide, please. So alternatively, we've also evaluated an often discussed strategy of instead trying to smooth the PV ramps directly at that individual plant level using storage. So here you can see how we simulated the operation of a battery that's used to limit these ramps from an individual PV plant. And on a partly cloudy day, that's on the right-hand side there, you can see that the battery has to be rapidly charged and discharged in order to limit the ramp that would come from the PV and battery system. And in this case, we designed the battery to try to limit that ramp to about 5% of the PV capacity per minute. And then the battery size itself, the capacity of the battery, was sized similar to the PV plant. So in this case, it was like a 75 kilowatt PV plant. And so we also had similarly like a 75 kilowatt battery. But the amount of energy that that battery needed to store was relatively small. So at full power, that battery would be completely discharged in 15 minutes. And that was sufficient to be able to cover all of these conditions, including this partly cloudy day where you saw a lot of rapid output changes from the passing clouds. Next slide, please. So we took that battery dispatch profile and the characteristics of that battery in terms of the dimensioning of it, and sort of ran an analysis where we would look at different ramp limits that we'd be looking at, and use this on different PV profiles. We put that into NREL's SAM model, which has the ability to reflect some of the battery operations and some of the degradation that might occur as you start to cycle batteries. And then we use that to then calculate what the total system costs would be, how often that battery would be degraded and then need to be replaced, and so on. And really that replacement comes from that cycling of the battery, that it can be costly to really cycle that battery very quickly. And again, in this case, we're talking about something like a lithium ion battery providing this service. I think it was really helpful to hear Jeremy's presentation before this, because the degradation that you see for providing the same service here will really depend on what sort of technology you're using. And we're focusing on lithium ion batteries, which will degrade under that cycling. Next slide. So what we did was we then used this model to then estimate the incremental increase in the cost of a PV system due to this additional battery equipment cost that you would add on to that PV plant to provide this ramp control. And we looked at this for different levels of stringency of that maximum ramp rate. So the more stringent you were, the more you wanted to really reduce those ramps and smooth out the output of that PV plant, the more you'd have to add additional battery equipment. In particular, you were increasing the duration of that battery to provide that ramp control. What that meant was that in order to meet that higher ramp rate limit, or sort of more stringent ramp rate limit, you would increase the initial cost of this. And if we look at what the cost would be per megawatt hour of solar generation, we estimated that this using the battery to do the smoothing function would range from about $10 per megawatt hour to $40 a megawatt hour of additional costs, depending on the degree of smoothing that you're requiring. One other interesting finding from this chart that you can see here is that the costs were higher when we looked at this for just this small 75 kilowatt PV system using PV data from the city of Tallahassee. So that's what's shown in the orange bars. And that's relative to the blue bars, which are 12.5 megawatt PV system that was located in Jacksonville. And presumably the lower cost that we see here for that larger plant happens because there was less need for the batteries to be rapidly cycled to provide that smoothing, because even within that single power plant, there was already some smoothing that happens. There's already some effective aggregation that smooths out the output of those cloud-induced fluctuations. And so the resulting sort of changes in output that had to be provided by the storage asset were less for that larger plant, for that larger footprint plant. And so therefore we cycled the battery less, we ended up needing to replace that battery less often, and then therefore the costs of doing that were somewhat less. So the main takeaway from this analysis that we saw was just to say, if you compare this cost here to what we've seen from some of those integration costs, is that although you can take storage and try to smooth the output of an individual plant, it can be sometimes easier and more cost-effective to manage the aggregate variability at the balancing authority level first. And once you've sort of aggregated that up, then you take that residual amount that's left, and that's what you would use flexible resources to try to address. And that might come from storage, might come from other resources that you have on the grid. So now go ahead and go to the next slide. I'll now turn to the other issue related to integration, which is this lower contribution of variable renewables to resource adequacy targets. Again, I'll just sort of start off by introducing the concept and then discuss some findings from research on using storage to contribute to resource adequacy. Really, one of the things that we've seen in a lot of studies is that the contribution of renewable resources to resource adequacy targets depends on the production during times when there's the highest risk of insufficient generation to meet demand. And with historical low penetration levels of wind and solar, these periods of highest risk of outages, that was often occurring in the mid-afternoon peak peak summer days. And so this is showing some analysis from MISO. And so if you were to look at historic levels of risk, that would tend to be kind of concentrated in this time around 3 o'clock in the afternoon. And then the charts on the left show that the renewable production that was happening at these lower penetration levels would be somewhat high for solar penetration. That's in the yellow lines. You'd see that you'd not do too bad of lining up with those times of high system risk at low penetration levels. And then wind was somewhat worse in that it tended to produce less during the middle of a summer day than it would do at nighttime. So then if you were to take that low penetration level, look at the production of solar during those times of high risk, and then use that to calculate what the contribution of solar would be to meeting those resource adequacy targets, which is what's shown on the right, you would find a capacity credit of solar that might be as high as about 60% of its nameplate capacity. So it means if you had 100 megawatts of PV, you might count 60 megawatts of that towards helping you to meet your resource adequacy targets. While wind, under those same conditions, would only get something like a 20% capacity credit. And then the method that's being used here in particular, and why it's being labeled ELCC, is that they're using something called, they're using a probabilistic model of risk of outages and calculating something that's called the effective load carrying capability. So this is sort of somewhat seen as sort of the gold standard of how you might calculate the contribution of different resources to resource adequacy. One of the important things that a model like this can capture is that as you start to increase the share of renewables, that time of the period of when you'd have the highest risk can start to shift. And in particular, it shifts away from those traditional times in the afternoon and increasingly goes towards early evening after the sun has set. What this does is that means that now the timing of solar production, for example, in the early evening is going down towards 0. And so the incremental capacity credit of additional storage at that point can start to decline very rapidly. And so you can see as you add more and more solar, that capacity credit would decline from that high of 60% to dropping below even the level that we saw of wind at low penetration levels. Now wind, because it's not necessarily well correlated with that peak in the first place, and it's sort of distributed a little bit more over all hours of the year, doesn't tend to push the peaks in those ways as much. And so, in some cases, you could even see that as you push that peak towards the evening, that might actually increase the contribution that you're getting from wind to some degree. So there might be some sort of synergies that occur with those two. But aside from that, now what we're going to talk about in the next slide is to then start to see how could storage play a role in helping to increase those resource adequacy contributions of renewable resources. One of the challenges that we faced with starting to look into this literature and the methods for doing that is to answer the question of how would you actually dispatch that storage if its primary role is related to that resource adequacy function. And so what we did in our research is we developed a simple and fast algorithm that could be used to dispatch storage such that it would maximize its capacity credit. This particular method builds on an approximation of the capacity credit that NREL uses in some of their resource planning models, such as the REEDS model also. And what it does is that it really focuses in on how well the resource is able to decrease the peak net load periods. In this case, it's in the top 100 peak net load hours. And so our algorithm is basically going to take storage and try to dispatch it in a way that would maximize its production during those peak net load hours, accounting for any shifts that might occur as we add more storage or as we add more solar and so on. So we're gonna track what's happening with that and make sure that we're always dispatching the storage in order to maximize its capacity credit under those conditions. Next slide. So we took that approach that we developed, which was a fairly simple and fast tool that we could use that didn't require anything in terms of proprietary data. And we went and validated that by comparing it to an approach where a utility who had access to state-of-the-art models and then also the data that would be required to run one of those models based off of their own utility system. And we effectively benchmarked our method against theirs by using the exact same net load data and solar production data and so on, and then use that to calculate the capacity credit of storage and benchmark that against the dashed lines here, which are the results directly from that utility using their own tools and methods. And one of the things that you see that's interesting is that both of these methods show that as you increase the amount of storage that's being deployed in the system, that the capacity of storage can also start to decrease. And this can happen because as you add more and more storage, the remaining peak that has to be reduced by that next increment of storage starts to get wider and wider. So you start off by sort of reducing those top kind of narrow peaks, but then as you've done that, the remaining peak gets wider and wider, and so that requires longer and longer duration storage. Or if you're just having 4 hours of duration, the capacity credit of that 4-hour duration storage starts to decrease. The other things that both of these models showed was that if you have a higher share of solar in your power system, then one of the things that high amounts of solar can tend to do is that it narrows those net load peaks. And the previous slide also showed that to some degree with the data from MISO. If you have narrower net load peaks, then those are somewhat easier to meet with that 4-hour duration storage. And therefore, the capacity credit of storage with high solar, which was shown by the red lines, is actually going to be somewhat higher than the capacity credit of storage in the exact same system with lower penetrations of solar, which are shown by the blue lines. And again, the main purpose of this was to just validate our method that we had used. And then in the next slide, what we'll do is we'll take that same approach and we'll start to evaluate the capacity credit of different configurations of solar and storage. Next slide, please. So if you had a solar and storage system and you wanted to combine those two together, you have a different configuration options that you could evaluate. So we start off by basically just having these completely independent. We have a PV plant and a storage plant. They share no equipment. They don't have any sort of shared infrastructure, so there's no point of interconnection limit or anything like that that constrains their output. And also we allow that storage asset to go ahead and charge and discharge from the grid as needed. And so that would be our sort of our baseline configuration. And then if we brought those two together into the same plant, we have a couple of choices that we can also make and how we do that. So one option is that we can connect those PV and storage both together on the DC side, which means that we're sharing an inverter, but then still allow that storage to charge or discharge from the grid. So that's what we call a loosely coupled configuration. So they're sharing some inverter, but the storage is charging from the grid if it needs to. And then in the tightly coupled configuration, we again connect the battery and the PV plants on the DC side and share that equipment. But then we only allow the storage to charge from the PV plant now. So this is the tightly coupled because we're restricting it to only charge from storage. And so our questions with this were just to go through and see how these different choices about configurations would impact the capacity credit of this asset. Next slide, please. And what we found, one of the things you see here is that the capacity credit of storage really depends on its duration. So the x-axis here is showing different durations of that same storage asset, and the blue line is the capacity credit of storage by itself. And so as you increase the duration of that, you're adding more and more energy to that system, the capacity credit will go up and start to sort of plateau after you've hit about 4 or 5 hours of duration. If we have an independent system, then we just effectively take that storage capacity credit and we add on top of it the solar capacity credit. And you can see what happens there in the red line when we have those independent assets. And then what you can see is that if you start to bring these things together and you have any sort of shared infrastructure, like a shared inverter, or you have a shared point of interconnection limit, like you do in these green and purple lines, then one of the things that can happen is that you can start to run into the situation where your solar would be discharging at the same time as your storage potentially, and effectively cap what the total capacity credit might be of that solar and storage asset. And so that's one thing that's important to keep in mind as you bring these together, is that any sort of limitations like that, it can effectively impose a constraint that might limit the flexibility of the storage that you're able to get out of it. And so you want to be cognizant of that and sort of design that system accordingly. The other thing that was interesting, if we focus, if you stay on that same slide, if you focus on the results on the chart on the right, this is what we found with the utility in Jacksonville, where they tend to have both high load in the summer, but then also with very narrow high winter peak events that happen when you have a storm that comes through and there's a lot of electrical heating demand that would suddenly spike up during that time. And so one of the things that we see here is that in that case, if we are restricting the storage to only charge from solar, in that tightly coupled case in the green line, we could end up in situations where during these winter cold weather events, the solar would be insufficient to charge the storage, and we'd actually end up lowering our capacity credit to some degree. These are not large effects that we're seeing necessarily, but again, just something that's important to keep in mind and to think about that when you're designing these systems and thinking about whether or not you want to be restricting the way that the battery is operated and where it can charge and discharge from. And just overall, the key message from this is that storage can contribute to resource adequacy, but the specific contribution of it is really going to depend on these configuration options. Next slide. So for the last part of this presentation, I'm going to turn now and sort of widen the lens a little bit to talk about the commercial activity that we've been seeing for these combined renewable energy and storage plants, and really start to talk a little bit about these broader motivations for deployment. Next slide. And one of the things you can see is that the overall motivations for hybrid plants do extend well beyond just some of the narrow issues that we've talked about so far. One of the important motivators for some of these hybrid plants is the investment tax credit. And so federal policy is playing a role here. And what happens is that the storage capital costs can be reduced by this investment tax credit as long as the storage is being charged from a renewable resource. If you had that same standalone storage asset and it wasn't being charged from a renewable resource, it would not be eligible for that same incentive. And there are some nuances to that. It's basically that the minimum amount that you have to be charged is 75%, and then you prorate sort of the investment tax credit for anything below 100% charging of this from the renewable plant. And if you're fully charging, you get that full 30% reduction in your capital costs. But aside from these policy considerations, there are some true cost reductions that can come from things like shared permitting costs, shared interconnection costs, and also perhaps sort of the ability to accelerate your interconnection process by having a single process to go through rather than multiple different assets. And then there's other equipment, again, that you might be able to share between these equipment and reduce, between these assets and reduce their costs. The other thing that's interesting to think about is that when you do have solar and storage connecting on that DC side, that there's a potential that you have some energy that would otherwise be clipped from those PV panels because the panel might be oversized relative to the inverter. And if you place storage on that DC side, you might be able to capture some of that clipped energy and then use that later. So that can be another motivator for some of these plants. On the other hand, there might be some opportunities that you might forego. So if you're taking that storage asset and you're deciding to site it with a renewable generator, there might be other places within the system where you might be closer to loads or where you could potentially defer some of these transmission investments and so on, that you'd sort of like lose out on that opportunity potentially. So it's important to kind of think about, is there any opportunity cost associated with bringing that storage into the location of the renewable plant? And then again, we've talked a little bit about how there might be some operational flexibility that's limited because of some constraints that you would apply on that storage when it's in a hybrid function versus if it was just independent on the grid. And then finally, there is some regulatory uncertainty. In particular, there are some market rules for interconnecting hybrid resources and for participation models in wholesale markets that they continue to evolve, and there's a lot of really interesting discussions happening on those that are going to be important for making the business case for some of these. Next slide. Okay, so now we'll take one quick poll, which is just to ask a question of which model for energy storage deployment is or is likely to be the most used in your state. Option A is as a standalone front of the meter asset. Option B is as a behind the meter asset. And option C is a hybrid with a co-located generator. Okay, now there we go, show the results. Okay, and so there's a lot of interest in these hybrid co-located with generators in these results, and also a lot of interest in the behind the meter asset and a little bit less in the standalone configuration. So your poll results, go ahead and go to the next slide, please, are in line with what we're seeing with commercial interest, and that commercial interest in these hybrid plants is really growing. And I'll go through in the next couple slides some data that shows that growing interest based on shifting activity in interconnection queues. And one of the things you see is that interconnection queues across the country are dominated by wind and solar. And there's also a growing interest in storage in these interconnection queues. And that storage will be in some of these standalone, but also in the hybrid options with wind and solar plants. The hybrid portion of this is shown in the hatched bars there, where that's the quantity that has storage paired with it. Now, with these interconnection queues, it's important to keep in mind not all of this is going to be built, but what it does is give us sort of a sense of the activity that's in the development pipeline and some of the trends that are taking place in the industry. Next slide. The bulk of this hybrid activity is happening with solar and storage, and most of that is happening in the Western United States, where we do see increasing levels of solar penetration. And for solar, if you look at what's the sizing of these, the batteries tend to be sized about 66% of the nameplate capacity of the solar plant. So they're fairly large batteries relative to the solar plant. Whereas on the other hand, for wind plants, those batteries are sized at a smaller size at only about 27% of the wind nameplate capacity. Next slide. Another interesting finding is that about 2/3 of the solar and about half of the wind in the California ISO queue now has storage with it. And if you look at just what came into the queue in 2019, it's even higher. It's like something like 95% of what was added in just 2019 had storage with the solar plants. If we were to go across the country to other locations, you see growing interest in these hybrids also. MISO, for example, about 17% of the proposed solar capacity would be also hybridizing with storage, whereas only about 2% of the wind in MISO would be adding storage with it. And that might, again, reflect some of these issues associated with the investment tax credit, perhaps, or just some of these synergies that we see with resource adequacy and solar. So next slide. In these last few slides, I'm just going to go ahead and summarize some of the limited cost data that we have that we've collected for a small subset of these projects. And these are projects that have signed PPAs. And then we also did some preliminary modeling of the value of hybrids using historical market prices. Next slide. If we look at this cost data for, again, a subset of the projects that we saw before, one clear trend is that the cost of solar and storage hybrids are really declining. the projects in the Southwest that have signed agreements, some of them have been signed at as low as the sort of the $20 to $30 per megawatt hour range. If we were to look at Hawaii, we see projects that are quite a bit more expensive than this, but they are following sort of a similar downward trend in the costs. Next slide. So for a small subset of these projects that we have cost information, we've also been able to tease out just what the additional incremental cost is of the battery. And one of the things you see is that this cost adder of adding storage to the PV system increases as that battery gets larger and larger relative to the PV plant capacity. If we were to look at a 4-hour duration battery, again, 4-hour duration gets you sort of close to that 100% capacity credit. And if that's sized to about 50% of the PV nameplate capacity, that would increase the costs of a PV plant by about $10 per megawatt hour based off of what we've seen from these signed PPA prices. Next slide. So we were interested in looking at the other side of this and thinking about what's the additional market value you might get from adding this storage. So here we're going to use historical market prices to estimate the additional value of adding storage to a solar plant or adding storage to a wind plant. Now, rather than dedicating this battery to doing smoothing of the variable renewable generator or doing something where we're just focusing on resource adequacy, in this analysis, we're dispatching this battery to maximize the revenue of that battery or that battery and hybrid system. And we're subjecting it to constraints that might be things about the limited point of interconnection, or we might restrict the battery to just charge from the renewable generator. And what we find in these results here is that the addition of a battery can increase the value of a wind or solar plant in California significantly more than what we saw in Texas. And the reasons for this increase in value in California in particular come from, in part, this increase in capacity value. So again, a 4-hour storage gets 100% capacity credit in California, and therefore is able to qualify for some of these resource adequacy contracts. And so we valued it at the price of those contracts. We also see that there's a lot of volatility in California prices during this period of 2016 to 2018. And part of that is driven by the fact that we have sort of lower prices during the time we might call the belly of the duck, and then increasing prices at the times of the end of the ramp when we have the high net loads sort of at the neck of the duck. And so that increased volatility would also then increase the value of storage that can maximize its revenue by dispatching against those prices. So if we compare these estimates of the increase in value of adding storage to the previous estimate that we had of the increase in cost of about $10 per megawatt hour for a similar configuration, then in California, that battery would start to look fairly attractive. But in Texas, it would be less so because of that lower volatility in prices during that particular historical year. Next slide. So we can look at that exact same situation just from somewhat of a different lens here. And so this is, again, the same data just presented in a different way, which is, in this case, we've thought about this idea that you might have a standalone renewable generator, but you could also have a standalone storage asset that's out there. And so we want to compare the value of those two standalone assets, where now in the standalone storage, you're just dispatching it to maximize its revenue, whatever, based on the grid prices. And then compare that to the hybrid plant, where we're now bringing those together and potentially subjecting them to some constraints. And that, again, could be things like the point of interconnection limit. We might be restricting the battery to only charge from the solar or wind in this case. You can see that there's a slight reduction that you would see in the value because of that, but it wasn't dramatic. It was somewhere on the order of about 7 to 11% of the value would be reduced by hybridizing. And so what you want to do is, if there are some of those value reductions, you want to compare that to those cost synergies we talked about from things like the investment tax credit or reducing interconnection costs, other factors like that might be on the plus side for doing that. Okay, next slide. So I'll just wrap it up here. I just have a few questions that I'll run through that states might ask utilities, and this just sort of summarizes some of what I've talked about today. But so as you're bringing storage and hybrids into these planning discussions, you might ask questions like, how do you take advantage of this geographic diversity to manage challenges with variability and uncertainty? And we saw that a variability at a plant level can be much greater than the variability when you kind of aggregate over the footprint of a utility. And managing this aggregate output requires fewer reserves and it can be less costly. Another question is how much storage is needed to manage the aggregate variability and uncertainty compared to managing at each individual plant. And so if you're using that storage to manage variability and uncertainty, less storage may be needed, and the storage would be cycled less often if you're doing that sort of at that aggregate ramp level, rather than trying, again, to kind of do that at the individual plant. Another question to ask is how your resource adequacy assessments account for any potential changes in the contribution of resources with increased deployment. We've seen that particularly for solar, the resource adequacy contribution can decline with increasing penetration. And these capacity accreditation methods that are being used in practice should really try to account for this decline and the potential implications that we might see from this shifting period of high risk. Again, sort of a trend towards from summer afternoons into the early evenings. And then another question would be, how do the costs and benefits of hybrid configurations compare to these standalone configurations? And just again, whenever you're evaluating these hybrids, it might be helpful to just sort of think about this, the attractiveness of that asset relative to what it would look like if you were to do this with a standalone configuration. And is there any sort of opportunity cost, or are there some synergies? So that's another question you might ask is, what are some of these potential cost or value synergies of hybrids that you're accounting for in your planning and procurement? And again, some of these things might come from reducing costs through the ITC, might come from reducing costs by sharing equipment or interconnection, and which of these are sort of being included or drive some of the evaluation. And then finally, one other question is that if you do allow or prevent grid charging for hybrids, that might have some consequences for it. It might have consequences on the value side, but it also might affect things with eligibility for state policies. And so I think that's just something to be thinking about, is that if you do allow this storage to charge sometimes from the grid, that can potentially increase its value and increase its flexibility, but that might have some impacts on eligibility for renewable portfolio standards or clean energy standards. It's important to consider. Okay, and then I think the last slides are just some summary resources if you're interested in following up on some of those documents. Thanks.